And so, last but not least, we have our conservation of momentum problems. These were arguably some of the most challenging problems that we'll have for the entire school year, only because of how it is structured. If we are not careful about where we put our variables, this will get quite confusing. If we're not careful about what collision is occurring, we will be confused. So make sure you are doing the hard part first, which is finding the correct variables. Once you recognize that it is a collision, what you're going to do is split your question into before and after the collision. Now, if you have Desmos, there's arguably an easier way to get through these problems. It just depends on your comfortability. For example, this collision says they move off together, which ensures that this is an inelastic collision. And because it's inelastic, well, there's a specific equation we need to use where we have m1 v1 plus m2 v2 equals the combination of both masses and their final velocity. Which should make sense, right? If I hit someone and I pick them up, my mass is increased and my velocity should be changed. If I go to tackle someone while I'm playing some sport, our velocities should change because our masses have now combined. All right, easy enough. Now, if you put this into Desmos, my only suggestion is that you make a small change. I'll write this change here. All right. M1 V1 plus M2 V2 equals M1 plus M2 V3. And that V3 allows you to actually use that as a variable because it doesn't recognize VF very well. In this question, you would actually turn V3. Oh, not V3. V3 is not what's going to change. You're looking for VI, V1. If you put this into Desmos and make V1 your X value, once you plug in all your other numbers, look for the X-intercept. The X-intercept will tell you what your answer is. One more time. Here's your base equation. Right? Base equation. Here's the equation you would put into Desmos, where VF becomes V3. Once you have this into Desmos, graphing calculator, turn whatever variable you need into X. For example, this problem has you looking for the initial speed of the van. That is V1. You get initial speed of the van. The van was the first mass, so that is V1. We're going to swap V1 with X. Again, we're going to swap V1 with X. Because once we plug all the other numbers in, that X-intercept will give us our answer. Now, that's a lot of explaining. Let's say we don't have the graphing calculator and we kind of just need to figure this out without it. Well, then we want to break our question into two parts. Before the collision and after the collision. And after the collision, we know a couple things. Right? They move off together, so their masses should combine. That gives you 3,475. So the total mass is 3,475. The final velocity is 8.5. And then because we have both of those, we should be able to find the momentum, but I don't have a nearby calculator, so just make sure you use that. Oh, let me organize this properly. That should be, yeah. You can solve for that. Now, before the collision, let's look at this. Before our collision, we had two vehicles. One was moving, one was at rest. Well, let us organize this. M1 is 2575. M2 is 900. V1 We don't know. Let me adjust that. That's our goal. V1 is our goal. V2, well, we know it because it says at rest. At rest means not moving. So that should be 0. Which means its momentum should be 0. Which is going to be important later. Now, if we use our big old brains, we can make one big leap. If the momentum of the compact car is 0, then that means all of the momentum had to come from one thing. Can we figure out where the momentum came from? Well, hope so. Well, that means all the momentum had to come from the van. Well, that means we should get this. So go ahead and take a moment, see if you can solve that out and find that initial velocity. And so hopefully you were able to get the same answers I was able to get. The total momentum should have been 29,537.5. That leaves all of that momentum to go to the van. Once you have gotten this far, you want to divide the momentum by the mass of the van. Again, once you've gotten this far, divide the momentum by the mass of the van. You should get 11.47. Now, here's to be honest. This problem took about 7-8 minutes, which is just frankly too long. Now, it might have been less than that. Maybe I'm being dramatic. But if you look at it before and after, it will take you more time because of the steps you have to take. You're looking for the total momentum, and then you're working backwards. If you don't want to take this much time going through these problems, what you need to do is get better at isolating the variable you need, or just practice that Desmos method. Like Desmos, whatever you don't know is an x, and then you go out and find the x-intercept after you plug in all your values. If you do this before and after, just expect it to take a while. Now, before we move on to the next question, I want to at least show you what it looks like if you just isolate for V1. Because if you can do that, everything else gets a lot easier, just because you're not doing as much in comparison. So, like before, our goal is to get V1 by itself. What we can do is, let's say we have all this junk in the way. The first junk we want to get rid of is this M2, V2. We subtract it from one side and put it on the other. All right, cool. After that, well, we still have this bit of junk attached to it, and they are being multiplied. The opposite of multiplication is division. So divide M1 on both sides, and you end up with V1 equals M1 plus M2 V final minus M2 V2 over M1. Plug all your numbers in there, problem is solved, nothing really to worry about. But that requires you to be able to isolate for the variable initially and, well, be good at your old algebra. Yeah, that would be the fastest way for me. If you want to practice doing it this way, I can show you in the next problem. And after this, plug your numbers in, you're done. Best part is that's 0, so it's really just this. And no, the M1s do not cancel. No, the M1s do not cancel. All right, question 2. Let's see if I can do it the short way, and then I'll show you the other way. So we have, quite a few things. A hockey puck, mass 0.21 kilograms, moving at 35 meters per second, strikes an octopus thrown on the ice by a fan. The octopus has a mass of 0.265 kilograms. The octopus and the puck slide off together. Find their velocity. Okay. Slide off together means we have another inelastic equation, right? Another inelastic collision. So that means inelastic, M1 V1 equals, not equals, plus M2 V2 equals the masses put together, and then your final velocity. Well, we're looking for the velocity in the end, which means we're just trying to get VF. Now, it does not say the velocity of the octopus, so we're going to assume the velocity of the octopus is 0, the initial velocity anyway. Let's assume that's 0, which means all of that goes away. V2 is 0, so that means that entire first term goes away. Well, what is in the way of getting the final velocity by itself? It's all of this, right? M1 plus M2. So we're going to divide that to the other side. So what are we left with? We're left with the idea that your final velocity should be equal to M1 V1 over the total mass. Plug your numbers in, problem solved. All right, there's also the Desmos way. Remember, instead of having VF, you instead use V3. Wrong color. Because we do not know VF, that becomes your X. Plug in all your other values, see what that X becomes due to the X-intercept. Now, part of me doesn't want to do the before and after one, just because how long it would take. The idea is that you find the total momentum at the start. So before the collision, what is your total momentum? And they use that total momentum to look at what happened after the collision. Because they're moving together, so the total mass should add up to not much, 4.8, 0.48. And then the octopus had no momentum, so we can almost ignore it. All right, so M2 was 0.265. The initial velocity was 0. Its momentum is 0. So all we care about is the momentum off of the puck. 0.215. V1 was 35. The momentum from there should be something really small. Let's see, we get 0.215 times 35, 7.52, well, 7.53. So then you use this momentum, so let me circle it. you use that momentum and put it at the end, because the entire momentum of the system should equal 7.53 because there's nothing coming from your octopus. So, 7.53. Divide these two, because remember, your velocity just ends up as momentum over the mass. So you get momentum divided by 0.48. You get 15. I'm not saying that number. I should have gotten rid of this. But yeah, I've shown you the three methods. Method 1, isolate for the final velocity and then plug in afterwards. Method 2, type in your equation, the equation you want to use anyway, into Desmos, and whatever variable you do not know, just make it an X. And last but not least, let's say we're just in desperate times, look at before the collision and after the collision, and then figure out what's going on. All right, so I'm going to do question 3, and that might be it, because looking at time, we've already gone on for long enough. So the first two problems involved inelastic collisions. Now let's look at our elastic collision. Elastic meaning they bounce off each other or they do not move together. Again, this is our elastic problem. All right, if you're not asleep by now, hopefully this will put you to sleep because of how long it's going to be. Haha. So we have a bullet, we have the bullet speed, we have a wooden block. So bullet, mass, bullet speed, wooden block. Bullet passes through the block, leaving at 275 meters per second. That leaving section, again, the bullet passes through the block, leaving at some speed. That's what makes it elastic. They do not move together. At no point does it says they are together. Right. So the block was at rest. All right, cool. When it was hit, how fast is it moving when the bullet leaves? So this is asking about the speed of the block after the bullet leaves, because there's some speed loss. The speed must have gone to something. All right, so because this is an elastic problem, too big. So M1 V1 plus M2 V2 must equal, well, M1 V1F plus M2 V2F. We're just saying that, hey, whatever the momentum was at the start should be there at the end. And because they're not stuck together, they should have individual speeds. Right? And because they're not stuck together, they should have individual speeds. All right, well, let's see what we can do here. If you put this into Desmos, what you're going to do is, instead of putting V1F, V2F, yours is going to look like M1 V3 plus M2 V4. All right, so just be careful. We're swapping out the subscript of F, final, to just a subscript of 3 and 4. They represent the same thing. We're just trying to, simplify it for Desmos. Again, if you're using Desmos, we're going to look for not V3, because V3 is the speed of the bullet, right? Mass 1 is the bullet, speed of the bullet as it leaves should be 275. We're looking for V4, which becomes your X. Plug everything else in, we're done. Super upside is that 0. So you can almost ignore that whole term. All right. So then if you're using Desmos, you probably already have the answer. But for those who aren't using the Desmos process, let's use our big old brains and solve for v2f. Let's solve for the velocity of the block after the collision. So we have a bunch of stuff in the way. How do we get rid of the stuff? Well, first off, let's subtract that m1 v1f out of it. And then we're going to divide by m2. Again, we subtracted m1 v1f and then divided by m2. Again, super quick. The new setup is going to look like m1 v1 plus m2 v2 minus m1 v1f. And once again, no. M2 does not just disappear. It does not cancel out. Again, M2 does not just disappear. It does not cancel out. All right. But you can plug your numbers in, problem solved. The interesting thing here is, and if you notice, again, takes a bit of eye, this is really just the change in velocity of the bullet and then the ratio between the mass of the bullet and the mass of the block. Because that term goes away because V2 is 0. And if you look closely, this is the final velocity and the initial velocity of the bullet. Their masses are going to be constant, so you can just pull that out. So it's the ratio of M1 and M2 multiplied by the change in velocity. Which should make sense. If I am punching something heavier than me, it should not move as much because I have less mass than that object. The bullet has less mass than the block. So even if it hits super fast, that doesn't mean the block is going to magically fly off at like 300 meters per second. It's not going to happen because the bullet does not have enough mass to do that. But I digress. And let's say Desmos wasn't fun for you and this just looks like a bunch of scribbles. We still do before and after. Just be prepared. It'll take some time. Before the collision, after the collision. Well, before the collision, and when you do any of these, that bullet mass is not correct. The mass of that bullet is not correct. We don't use grams, we use kilograms. So M1 should be 0.025. V1 should be 375. That gets you some number. Now, M2, we don't really need because the momentum at the start of the block should be 0. So the momentum of the block at the start should be 0. Because it wasn't moving. All right, so let's find out what's the momentum of our bullet. 0.025 times 375. Okay. The momentum here is going to be 9.38. And so because this is the only momentum, that is also our final momentum. And so we're going to take this and move it to the end. Whee! Oh, well, before I do that, there's a little bit of work we have to do. Because unfortunately, it's not as simple as just sending it over. We have to figure out, well, how much momentum is left over after the bullet passes through. So M1 is still going to be 0.025, but its velocity has decreased to 275. So its new momentum, P1F, is not going to be 9.38, is it? .88. The new momentum of our bullet is now 6.88, which obviously does not equal 9.38. So then whatever's left over should be in our block. Right? That should make sense. If our bullet has this much momentum, but our total is different, the leftover momentum should go to our block. So M2, let's go through, should be 2.5. And the velocity we don't know. But the final the momentum should be the difference between 6.88 and 9.38. We got 2.5. So, that being said, seems like our final velocity is going to be momentum over mass, which is going to equal 1. And that's it. I guess not as dramatic as I thought it'd be. Just to clarify. Okay. And so this is why I heavily suggest that you use the Desmos method or use the isolation method, because if you do this before and after, does it take time, and you have to really think about what's going on. All right, well, I'm going to call it there. That should be everything you need, especially for conservation of momentum. There are other problems. I will scroll through, take some time, and try to solve them. If you have questions about how to solve them, feel free. Go ahead and leave comments. If there's anything that you think might be helpful to others who try to solve these problems, of course, leave it down there too. See ya. And of course, just pause it as you need so that you can solve them. They require the same equations we used earlier. And just make sure you have them written down.